Let's do this. Okay, so all we're doing here is classifying triangles. So this is a pretty short video. Really, there's only one big idea here, and that's that we can classify triangles in two different ways. It's essentially by their largest angle size. So does it have one big angle, one right angle, or are all the angles small? That's the big idea for angles. And for sides, there's a bigger underlying thing. We say we're classifying it by the number of congruent sides, but really we're conveying how many lines of symmetry the triangle has. So we're really saying, are there no lines of symmetry? Like there's no line down the middle where you fold it and it's the same on the left and right. Or if there's one line of symmetry, that's isosceles. Or if there's three lines of symmetry, that's equilateral. So that's really the underlying thing there, but we're just going to say we're going to name it by number of sides that are the same. So if there's one pair of congruent sides, so two sides of the three are congruent, we call it isosceles. But that's the big idea. We're either by congruent sides or by size of the largest angle is how we classify, and we can give every triangle a name for both. So every triangle can be called a isosceles or scalene or equilateral, and separately an angle, okay? All right, let's go. So here is, I'm going to zoom out here. We got three different names for both, right? So if we're classifying it by sides, we can either be scalene, none of the sides are congruent. So notice I show in the picture that we have 1 dash, 3 dash, and 2. That means those are different from each other. They are not congruent, okay? And then we have isosceles when one pair matches. Now, depending on the book, it's either exactly two sides match or at least two sides match. For the purposes of this video, I'm going to talk about at least two because the textbook we're using at this moment for this video is an inclusive definition. So what that means is out of all the isosceles triangles where two sides match, some of them have three sides matching. So every equilateral triangle is just a special case of isosceles, okay? All right, and then we go to equilateral. So equilateral triangle is when all three sides of a triangle match. And what we're going to get to later is whenever we have two sides matching, that means two angles match. It's the angles across. We're going to call this the base angle biconditional later on. But for now, we don't know that secret. The secrets of the universe remain hidden from us. And when three angles are the same, actually when three sides are the same, actually the three angles must be the same too. Again, we don't know these mysteries yet. So for now, we just name it by number of congruent sides. No sides congruent, scalene. Two are the same, isosceles. All three are the same, equilateral. Okay, and then over here, we just say, what's the largest angle? Okay, so if the largest angle in a triangle is 120 degrees, well then, this is obtuse because there is one obtuse angle. Now, you can't have two obtuse angles because if you did, that sum would be bigger than 180 and it would rip the triangle apart, right? Like here's bigger than 90 degrees and then here's another bigger than 90 degrees. Those two lines don't meet. So you can't have two obtuse angles. So at most you could have one. That would be an obtuse triangle. Or you could have a right angle. Again, you can't have two right angles because by the converse of the consecutive interior angles, these two lines would be parallel and they would never meet. So you can't have two right angles. So at most you could have one. Okay. And if that largest angle is a right angle, then we call this a right triangle. Finally, if all three angles are less than 90, all three angles are acute angles. That means the biggest angle, 70 degrees, is still less than 90. So again, we just look at the biggest angle. Biggest angle obtuse, biggest angle right, biggest angle acute. We just call the triangle obtuse right or acute. Okay. And just so you know, every triangle can be classified in both ways, right? So we can have a right isosceles triangle. So for example, here's a right triangle where its legs are the same. That's a right isosceles. We can have obtuse isosceles. So in other words, a really big angle, like 120 degrees, where these are the same. That's an obtuse isosceles triangle. We could have a right scalene triangle. So here's right, and we have 1, 2, 3. So each one can be named both by its angle and by its number of congruent sides. So we've got two separate words to describe each triangle, okay? All right, so we've got isosceles triangle vocab really quick before we jump into problems. Whenever we've got an isosceles triangle, right, we've got at least two sides are the same. Could be that special case equilateral, which is also an isosceles triangle. So here we go. We've got this vertex up at the top between the two congruent sides. And then the third side that's not congruent is called the base. Those are really the determinations, okay? So the angles along the base are called base angles. The angle at the vertex is called the vertex. And then we call the two congruent sides legs. Okay, so it doesn't matter, though, the orientation of this in space. Too commonly, kids think, well, you know, because the base is just the thing on the bottom. So in this right picture, they would call this one the base. That is not true. The thing that determines vocabulary in isosceles triangle is which sides are congruent. So here, these two sides being congruent mean these are the legs. The vertex and vertex angle are the one between the legs. And then that third side that's not congruent is the base. And then the two base angles are right there along the base, okay? But the two congruent sides are legs, and the other side is the base. And then we have base angles and vertex angles. Okay, all right, let's move on to just doing some problems. That's really it right here. Okay, here's how the book does it. I just put those in the notes. You could pause the video and look at how the book words it. Okay, let's do this. Draw a triangle that is isosceles and right. Well, if you draw a right triangle, and then say, well, you know, this is congruent to this, that's actually impossible. The reason is the shortest, well, we haven't gotten to why that's impossible yet, but the shortest distance from a line to a point not on the line is straight at it, perpendicular to it. So this distance is always shorter than this longer path to the line. And so the hypotenuse in a triangle is always the longest side. So it has to be longer for lots of reasons. Using Pythagorean theorem, we could prove it. Using shortest distance from a point to a line, we could prove it. So there's lots of ways to prove the hypotenuse is always going to be longer than this leg. So to do an isosceles right triangle, you have to have the hypotenuse by itself, and then it's the two legs that can be congruent. And actually, this is a special right triangle that we'll talk about when we get to trig. It's called a 45, 45, 90 triangle, and we'll use it all the time when we get to trig. Okay, sometimes, always, or never. Yes. Okay, equiangular triangles are also acute. Well, what's equiangular mean? So equa means equal, angular. So we've got a triangle where all three angles match. So are they acute? Well, if all three angles are the same and they add up to 180, we're actually going to prove that they add up to 180 in the next video. So yeah, we don't technically know that yet. Okay, maybe. Next section we will. We just take that 180 degrees and we divide it by three congruent angles, and we get every angle must be 6 degrees. So every equiangular triangle has three 60-degree angles. So the biggest angle is 60 degrees. So yeah, it is always acute. So that's always true. Okay, and right triangles are acute. Oh, well, that can't be, right? A right triangle is the way you're defining it by an angle. It has a right angle. So defining it by its angle, its largest angle is a right angle. So this is a right triangle 100% of the time. It never is an acute triangle. An acute triangle is when all three angles are less than 90. So yeah, that's never, just by the very definition of what a right triangle is, it can't be an acute triangle. All right, identify the obtuse triangles if, and it says MJK, so we've got it, that's shown in the picture, is the same as KLM. And this is the measure of MJK, so MJK is 126, so that's a whole 126 there, which means the other one too is 126, okay? And then it says JNM is 52, JNM is 52. So this is 52, which means this is 52, which means we can subtract the linear pair, and we get this is 128 up here, this is 128 here. We don't know how these angles get split here, and we don't know how these angles get split. We don't know enough about parallelograms and quadrilaterals yet, so it might be the case that we have some more obtuse triangles that we don't know about, but at least we know of a few here, and I'll highlight them in yellow. We know this triangle here and this triangle here because of the 128. Those are both obtuse. But then zoom out a little bit. We also know because of this 126 in the corner, we know this one is obtuse, and so is its mirror image, kind of. Not really a mirror image, but here is the other one on the bottom there. So let's name them all. So we got triangle MJK, triangle MLK, so those are the two larger ones. And then the two smaller ones are triangle J and K. Now notice the order doesn't matter with the triangle, because whether you're going clockwise or counterclockwise, you can actually put the points in any order on a triangle. With a four-sided figure, you have to go clockwise or counterclockwise, so you can't zigzag, but there is no zigzagging on a triangle. You're always, no matter what order you choose, you are going around the triangle. Kind of a cool thing to think about. And then we have M and L. So those are the only four that we know for sure. However, there might be more depending on how this angle gets split up. Maybe it gets split into like a 91 degrees and a 35 degrees, and then all of a sudden one of these two would also be an obtuse triangle, but we don't know that, so we'll leave it there. All right, over on the right, identify the right triangles if, and it says those two lines are parallel. It shows us that. It says GH is perpendicular to DF. Okay, so that means these are both right angles. And then GI is perpendicular to EF. So this is perpendicular to this. Okay, well, if this line is perpendicular to GH, and IJ is parallel to it, well then it means it's the same corresponding angle over here. So that's a right angle, so that's a right angle. So there are tons of right triangles here. So let's name a few, okay? Well, we have this one over here, and we have this one here, okay? And we have this one here. So let's start with those three, okay? I'm gonna just erase. Okay, so we got triangle IJF. We got triangle GDH and triangle GHJ. Okay, so that's three. Let's see what else. Are there any others based on those sides? Well, they didn't connect this side, so we can't do this triangle there. And this doesn't form a triangle. It goes out like past, so that doesn't form a triangle. Okay, let's see. So we got 1, 2 right angles used up, and we couldn't use this one over here in any way, I see, and we did this one. All right, so it looks like those 4 right angles at the bottom have been used up. Now let's try up here at the top. So we have this triangle, and then this one I don't see how we can use, right? It's part of this triangle, but it's not the actual angle of that triangle, and this one, again, only uses a part of that right angle. So, and they didn't connect like this to this to let us use that angle. So it looks like we've only got then triangle GEI. Sorry, I got something in my throat. Okay, and then let's go down. So now we're going to use some algebra. So it says find x, so in other words, find x and then some side lengths. If JMN is isosceles. And then when it says isosceles, it needs to tell you either which are the legs, which is the base, which is the vertex. So some vocabulary or extra explanation so you know which sides match. And then it goes ahead and says this. So JM is the same as that. Oh, those are the two that are equal. All right, so the work we'd show, then we go, oh, well, then that means by the very definition of an isosceles triangle, we know this is true. Okay, so we subtract the 2x from both sides, we add the 9 to both sides, and we get x is 4. We go back and plug it in, and hopefully it works out. We get 8 minus 5 is 3. We get, on the right here, we get 12 minus 9 is 3. Yes, we got 3 and 3. And then on the bottom, we plug in 4, and we get 4 minus 2 is 2. Okay, so we got all the side lengths. It checks out as an isosceles triangle, and we got x. All right, find all these if this is an equilateral triangle. So for an equilateral triangle, that means all 3 sides must match. So we could write 4x equals 2x plus 1 equals 6x minus 1. But really that's 3 separate statements, right? We're really saying these match, and we're saying these match, and we're saying 4x equals 6x minus 1, right? There's 3 pairs. There's this pair is the same, this pair is the same, and this pair is the same. Doesn't matter which one you solve. Any one of them will get you a solution, and then we'll plug it back in and just see if that solution works. Because who knows, maybe it's an impossible scenario, and we would say there's no solution. So we'll solve this one. So we'd minus 2x. We get 2x equals 1. We get x equals a half. Okay, so let's see if that works. Plugging it in, we get this side is 2. We get this side is 2 times a half is 1, plus 1 is 2. And on the bottom here, we get a half of 6 is 3, minus 1 is 2. So it works. So every side of the triangle is 2, and x is equal to 1/2. Okay, identify the indicated type of triangles in the figure. If, and it gives us all this, so AB and CD and DC and AC are all the same, and we have that right angle in the middle. So it says, where are all the right triangles? So the right triangles would just be 1, 2, 3, 4, because anytime one right angle is formed, its vertical angle is a right angle. 180 minus 90 is another 90, like linear pair, and same thing over here. So anytime we have perpendicular lines, it forms 4 right angles. So we know we have, for 22, we have ABG, BGD, we have triangle AGC, and we have triangle GCD. Okay, so for 23 obtuse triangles, well, I mean, it looks like, now we're having to go on kind of assumptions here, right? Like, we don't know what looks like obtuse triangles, so I don't like that it's asking this. I mean, we could assume like this is obtuse, maybe. We don't have enough information for that, because really this is a rhombus. So this rhombus could look like this, where those are obtuse, or the rhombus could look like this, where these are all right angles, and then that rhombus is a square, or it could look like an extreme the other way. So we don't have anything to go off of here. So I don't like that. So I'm going to say none for sure, but I'm guessing they wanted us to say this big triangle, this big triangle, this big triangle, this big triangle, something like that. But it's actually impossible that all 4 of those are obtuse, and we'll prove that later. So maybe they just wanted those 2, but I would say none for sure. We really have no idea. Okay, and so 24, so scalene, again, like none for sure, right? Like this could be a square where everything's symmetrical. So I'm going to say none for sure. I don't know what the book wants here, right? But we don't know any or scalene without any more information to say which sides are which. Like we would have to know that like this side and this side are different to know it's scalene. So we don't know that. However, we do know lots of isosceles triangles. So for 25, we do have a lot, right? Like what sides match here? Well, we have this pair, this pair, this pair, and this pair. So that we have 4 isosceles triangles. So the big triangles are ABD. We have triangle ABC. We have triangle ACD. And then we have triangle BCD. Okay, cool problem. Although 23 and 24, there's no way to identify those in the picture, so that's interesting. Okay, so find x and the measure of each side of the triangle if you want this. Okay, so it says this is isosceles. Again, that doesn't tell us which sides match. And then it says HG and G. Okay, so now we do know. So let's go ahead and do this. So here's my H. Nope, that's wrong. The G is the one on both sides. So I'm going to put the G up top. Who cares where it's on top? Let's put an HJG there. And we know HG is the same as JG. Oh, our isosceles triangle's on its side. It's impossible. The base is over here. What the heck? We're flipping space and time. Okay, anyways. So now GH is x plus 7. We got GJ is 3x minus 5. And we got the other side is x minus 1. So we know these are the sides that match. So we would definitely set up the equation to be this. Now we have one variable and one equation, which we can solve. Subtracting the x from both sides. Adding the 5 to both sides. Then we divide by 2. We get x is 6. Let's plug it in to make sure we didn't make any mistakes. So over here we get this is 13. Plugging in 6, we get that's 18 minus 5. That's also 13. Plugging 6 into the other one, we get this is 5. Nice. Worked out, okay? So it is isosceles. We found every side and x. Okay, so this one, it's equilateral. And oh, it's a word problem. And this is where we're ending, just these 2 word problems, okay? So it's equilateral. And it says, so we got this QRS, okay? Okay, and it says QR, so this side over here is 2 less than, so I'm just going to write, so 2 less than 2 times a number, right? I don't know what number. That's crazy, right? And over here it says RS is 6 more than a number. Okay. Oh, and it says the number, so the same number. So let's give that number a name. Let's call it I don't know. Let's call it X. And then now here we also have that same number X. Okay. And then the other one, let's see. QS is 10 less than 3 times, and again that same number. Okay, so here's X. All right, so again we can set up 3 different equations here. These two sides are the same, these two sides are the same, or these two are, because it's equilateral. So we know when it's equilateral that all the sides match. When we have one variable, in general we only need one equation to solve for it. Okay, so first I'm going to convert all these. So 10 less than, remember 10 less than is the one you have to be careful about because it's actually reverse order. So we start with the 3 times X, and then 10 less than that is minus 10, not 10 minus 3X. All right, 6 more than X. Again, the order isn't going to matter, but really it's saying start with the X and then 6 more than it. But 6 plus X, same thing. And then 2 less than, ooh, reverse that order, 2 times X. So we have 2X, and then 2 less than that is this. So we can set any 2 equal, and then we can just plug it into all 3 to make sure it works, okay? So let's just do, I don't know, these 2. Okay, so 2X minus 2 equals X plus 6. We subtract the X, we add the 2, we get X equals 8. Now let's plug it in and check. X equals 8, so this is 24 minus 10 is 14. Here, this is 8 plus 6 is 14. And over here, it's 16 minus 2 is 14. So check. It worked out. X is 8, and all the sides match. Okay, so this one's isosceles with some sides matching. I'm just going to draw a random JKL, and then we'll see what sides match. So KL matches LJ. Oh, again, it's on its side. No! Okay, JL is 5 less than, so I'm going to just write this 5 less than 2 to a number. So I'm going to call that number X, and we're going to do this again. Okay, so 5 less than, so 2 times the number is easy, that's 2X. And then 5 less than, so JL, we start with the 2X, and then we go less 5, so we take away 5. All right, and then it says JK is 3 more than the number. So we start with the number X, and then 3 more, so plus 3. And then the last one is 1 less than the number. Oh, well, so just the number minus 1. 1 less than the number. So KL is just X minus 1. Find the measure of each side. Okay, again, these are the 2 sides that match. So we're going to go X minus 1 equals 2X minus 5. We subtract the X from both sides. We add the 5 to both sides. And we end up getting X equals 4. So we plug that back in and let's see what we get. So this would be 3. This would be 8 minus 5 is 3. And then this would be 4 plus 3 is 7. So that's awesome. Now actually this is an impossible triangle, and we're going to investigate this in the future. But if you think about this, if this is 7 long and I have a 3 and a 3, that only makes a total distance of 6. That, like, imagine the river is 7 wide and you have 2 boards that are of length 3. That's not enough to get across that river. So actually, this is an impossible triangle. So the correct answer here would be no solution. But I'm guessing the book said, oh, the answers are 3, 3, and 7. But we're going to investigate in the future why that's not actually possible to create a triangle with those values. What a cool place to leave off. Like, what does the future hold? All right, guys, adios.